Hey everybody, this is Mr. Schultz here. We're going to take a look at 11.2.4 today. I'm going to try to summarize our start here, but statistical process control. So it says this in lesson 11.2.3, you check the quality of an item after it was manufactured, but we want to take a look at what happens if we can do that during the manufacturing process so that we can not produce a bunch of stuff and have to throw it away. So natural variation occurs in all manufacturing processes, no matter how precise, computerized, or state of the art. So they talk about an example here with ball bearings, and they say, okay, they need to be this big, plus or minus zero point 0.2 millimeters, which is a really tight tolerance there. And another good example of this, if you think about producing like a phone, like an iPhone or something, you have to have extremely tight tolerances there because if you produce like the camera lens and it's a little bit too big, well, then it's not going to fit in the housing. Or if the housing is too small, then the lens is going to fit. Or if things are off, then you're just going to have looseness in that. But even in those like hyper computerized, hyper tight tolerances, there is still a tolerance. There's still this kind of, this is the size that we're aiming for, plus or minus this. So that whole thing, and basically checking that like over time is a process called statistical process co- control. So the process needs to remain stable over time so that the output of or product of that process remains high quality. So in lesson 11.2.3, so last lesson, you verified the quality of it after it was manufactured. If the quality was poor, large quantities of the item had to be discarded or recycled at great expense. A fundamental tenet of manufacturing is that it's far less expensive to control the manufacturing process to catch and fix problems early than it is to test the quality of finished products that can no longer be fixed. So basically, that's what we're going to look at. Can we check the manufacturing process to make sure that we end up with those quality pieces so we don't have to throw stuff away? So let's jump in. So what's going to happen here is we're going to take a look at this number 1172 X bar control chart. So it's what this Burr Ice Company, and they're trying to make ice cubes that fit certain specifications so that they're useful to go into restaurants here. So they Burr keeps track of its process by making ice cubes and taking a sample of 10 ice cubes every hour and then plotting the mean size over time. Some of their data from yesterday is below here. So basically, we've got this chart here, and I'm going to quick show you this in the Texas Instrument because on the next screen, they have some of this type of stuff. And I'm just going to try to show that quick because we're actually going to end up using the student e-tool and Desmos, but I just want you to be able to see this. So in the TI calculator here, what we would do is we'd have to go into the lists and we'd have to go into edit and we'd have to go and get our data plugged into these lists. So you can see that I've got a few of these pieces logged in there through six, and you go through and you log all of the rest of those data points. So the hours in the first list, the mean cube size in the next list. And so then I need to stat plot this. So I already did some of this. So I turned this first stat plot on. So I'm just going to enter this and turn it on. And I'm going to have it be, instead of a scatter plot like this, I'm going to have it be more of like a line chart there. And then my X values are from list one, my Y values are from list two. It's in blue, and we graph it. And lo and behold, it doesn't show up because our numbers were big. They were like 270 plus. So then you'd have to go in here, you'd have to go into Zoom and zoom out and try to find this thing. This is part of what makes the TI calculator just a little bit more cumbersome here. So let's just take a look at the link that they gave us. So here we've got our student e-tool. And we're gonna jump in here. Boom, it's right there. They already entered the data. They've got it in this line thing. I think that's an important thing for you to know. So here, if you were to go and do this by hand, you would just add a table here and you'd enter your pieces of data here. I don't know, let's call this 3, 4, 3, 2, and 4. And then and right now it's got the dots. So you just click and hold there, and you could turn it into a line. Oops, I missed apparently. Turn it into a line, and then it will show up as a line right down there. So that's how you would do that process. And then you press the zoom and it'll jump right into that there. So how you get that line, just press and hold and then just check uh the line box or turn it off. So like here, if I turn it off, now it's just a scatter plot. Now it's a line plot. Okay, there we go. So we've got our data here. Let's jump back to our question now. So it says create a scatter plot with the mean cube size as a dependent, basically just saying and time as the dependent and time as the independence, so hours in the x, mean cube size in the y, and then go there. Okay, we did that because they already gave us that graph. Sweet. Next up, the process data is useful only if you know what size ice cubes are acceptable. So these specifications are called the upper control limit and lower control limit. I have also heard them called tolerances. And so, yeah, so they're looking for that mean size and plus or minus 100 millimeters from there. So add the control limits to your scatter plot. Okay, well, if it's supposed to be 250 plus or minus, well, then plus 100. My upper control limit would be 350. My lower would be 150. So basically, I need to add these lines which are at 350 and 150 to my scatter plot. Well, that's just as simple as saying, hey, y needs to equal 350, and there's my upper control limit, and then y needs to equal 150, and there's my lower control limit. If I want them to be the same color, just so we know what our limits are, there we go. So we've added our upper and lower control limits there, and there's that. So this type of chart here is called an X bar. And just to be clear, X bar here, that's the same thing as the mean slash average. So whenever you see X bar, it is talking about the mean or the average. So this type of chart is called an X bar or an average process control chart because it plots the mean or the average from the manufacturing process. Since all of the means are within the process control limits, this manufacturing process is said to be in control. Okay, so we did that. Let's move on to the next one. So now we're going to take a look at 73. Again, you can pull up the TI calculator to do this, or we can click on the student tool, and then we're going to make a process control chart of that. Well, guess what? It's really easy when they already make the chart for us. So we're just going to go down here, and we're going to click on 73, and look at that. We've got our process control chart. Check. We have done that first step. And it says, at which hour did the process go out of control? Well, we can take a guess that it's this, or we can do that upper and lower bounding. It's that same Burr ice cube company. So we are just setting up our upper and lower to check out. And hey, look, it's right here. So at hour number 15, it looks like it got out of control there. So at hour 15, it got out of control would be our answer there. So hour 15, and then it says what is something that might make this happen. It could be just a whole slew of things. It could be maybe there's a changeover and somebody missed something. It could be maybe an air conditioner or some sort of process like started to heat up, just anything that would melt ice and or um excuse me, not melt, because these are actually getting like larger in size. So anything that would end up making things cooler would end up doing that. So air conditioning, like kicking in the building or something like that, like maybe changing the building temperature a little bit. Something like that could do something like that. There are a bunch of options there. We're kind of just guessing. So let's move on to our next one, which is going to be question number 74. So 74. Same type of thing. So we're talking about Burr ice cubes again, and the mean is right below. Again, we're just going to jump straight to Desmos and go from there. So let's pull that up as we are speaking here. So taking a look at 74 now and pulling up this next student tool, we've got that all in there. So it says create the X bar chart. We have it right there. What do you notice about the process control chart that might be of concern to a quality control per person? Well, let's just set our upper and lower limit again. So here we are at 350, and here we are at 150. So we've got our kind of two lines here. Well, everything's in control, But you might notice that, like, hey, these are kind of like they're starting to kind of hop up, and there seems to be this kind of general trend, like it's going up, which kind of means that, like, hey, why would the engineers stop the process in the 19th hour? So stopping here because they're generally seeing this trend up. So they're still inside of the range, but it seems to be going up. It seems like it's just about to it could get out of control here. So in RB here, just general trend up and close to out of control. Of control. Okay, cool. So So even though the process is entirely within the process control limits, a process is considered out of control if 9 consecutive points lie above or below the center line of the process can control. What size ice cube is in the center between the UCL and the LCL? So the upper control limit, the lower control limit. And I guess I should say this. When talking about creating the X bar process chart, technically that does have your upper and lower limits on it, plus these points. So technically, I wasn't done when I just had the chart here. I also needed those two bars. So we need to find that. We need to find that mean again. If you remember it, it was 250, or otherwise just go halfway between your two limits here. So I'm just going to set my center line here, and that's going to be in green. And so if we have 9 consecutive points above, or I should say above or below. So here we're kind of bouncing around, but then right here we got 1, 2, 3, 4, 5, 6, 7, 8, 9 consecutive that are all in one range. In this case, above. They could be nine all 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 below the line, but all of that is reason to be considered out of control there because I've got 9 consecutive points that are doing that. So what size ice cube is between the UCL and the LCL? Again, they told us that was at 250. So add the center line, yep, and then make a conjecture about the context of problem to determine what may cause the 9 points of loss. It could just be machine failure. It could be some sort of a human error. It could be there. This is just again that same type of thing. Where we're just kind of like we're just kind of making a stab. We're trying to make a prediction here as to what's happening. So a bunch of different things here, but overall, the goal here is just to try to catch that process before you make all this stuff and then have to throw it away. So. This really short lesson, and guess what? That's the end of it. Review and preview, and that's everything that I got for you today. Have a good rest of your day. Bye bye.